Hello and welcome to the session on the critical section problem with Peterson's solution. Before we move forward, here is the learning outcome. At the end of this session, students will be able to uniquely identify the critical section problem. What is critical section problem? A critical section is a segment of code which can be accessed by a signal process at the specific point of time. The section consists of shared data resources that required to be accessed by other processes. Each process has a segment of code called critical section, in which the process may be changing common variables, updating a table, writing files, and so on. The important feature of the system is that when one process is executing in its critical section, no other processes is allowed to execute in its critical section, which means that no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that processes can use to cooperate. Each process must request permission to enter its critical section. The section of code implementing to this particular request is the entry section. The critical section may be followed by an exit section. The remaining code is remainder section. Here you can see the general structure of a typical process PI shown in this particular figure. The entry section and the exit section are enclosed in boxes to highlight these important segments of the code. A solution to the critical section problem satisfies the following three requirements or rules. First is mutual exclusion. If process PI is executing in its critical section, then no other processes can be executing in their critical sections. Second, progress. If no process is executing in its critical section and some processes wish to enter in their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which will enter its critical section next. And this selection cannot be postponed indefinitely. Third is bounded waiting. There exists a bound or a limit on the number of times that the other processes are allowed to enter their critical sections after a process has made a request to the enter its critical section and before that the request is granted. Here we assume that each process is executing at a non-zero speed. However, we can make no assumptions about the concerning the relative speed of the n processes. At a given point in time, many kernel mode processes they may be active in the operating system. As a result, the code implementing an operating system is subject to several possible race conditions. This list must be modified when a new file is opened or closed. If two processes were to open the file simultaneously, the separate updates to this list could result in the race condition. It is up to the kernel developers to ensure that the operating system is free from such race conditions. There are two general approaches which are used to handle critical sections in operating systems: preemptive kernels and non-preemptive kernels. A preemptive kernel allows a process to be preempted while it is running in its kernel mode. A non-preemptive kernel does not allow a process which is running in the kernel mode to be preempted. We cannot say the same about the preemptive kernels, so that they must be carefully designed to ensure that the shared kernel data are free from race condition. Preemptive kernels are especially difficult to design, because in such environment it is possible for two kernel mode processes to run simultaneously on different processors. A classical software based solutions to the critical section problem is Peterson's solution. The Peterson solution is restricted to two processes that alternate execution between their critical sections and the remainder sections. The processes, which are numbered P0 and P1, and when they are presenting the PI, we use Pj to denote the other process. Peterson solutions requires two processes to share the two data items as shown here in this slide: integer turn and boolean flag. The variable indicates whose turn it is to enter in the critical section, which means that if turn is equal to I, then process Pi is allowed to execute in its critical section. The flag array is used to indicate if the process is ready to enter in the critical section. For example, if flag I is true, then the value indicates that the Pi is ready to enter in its critical section. To enter the critical section, the process Pi first sets flag I to be true and then set turn to the value j. Then process wish to enter the critical section, and it can do so. Here we will prove the solution is correct. For that, we have to show that mutual exclusion is preserved. Second, the progress requirement is satisfied, and the third, bounded waiting requirement is met. To prove the property 1, we have to note that each Pi enters its critical section only if either flag j is equal to false or turn is equal to I. Here note that if both processes can executing in their critical sections at the same time, then flag 0 is equal to flag 1 is equal to true. These two observations shows that P0 and P1 could not have successfully executed there while the statements which are being about the same time. Here, once the process say Pj must have successfully executed the while statement, whereas Pi had to be execute at least one additional statement, that is turn is equal to j. To prove the properties second and third, here we have to note that process Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition flag j is equal to true and turn is equal to j. If Pj is not ready to enter the critical section, then the flag j is equal to false and Pi can enter in its critical section. If Pj has set flag j to true and it is executing in its while statement, then either turn is equal to I or turn is equal to j, and if turn is equal to I, then Pi will enter in its critical section, and if turn is equal to j, then Pj will enter to its critical section. And if once Pj exits, okay, however, once Pj exits in its critical section, then it will reset flag j to false and allowing process Pi enter to its critical section. If Pj resets flag j to true, it must also set turn to I. Here, since Pi does not change the value of the variable turn while executing the while statement, Pi will enter the critical section, which is a progress one, after at the most one entry by Pj, which is in a bounded waiting. Here, pause the video, think and answer. The answer is B. Here is my reference. Thank you.